Welcome to Power Players by Origis. Critical thinking to deliver the promise of clean energy.
All right, welcome to another episode of Power Players. Today we have Rhone Resch from president and founder, right, of Solarlytics. We're going to talk a little bit about DC Health and some of your contributions recently that a lot of us have looked at and read. Welcome to Power Players, Rhone.
Thanks for having me, Michael.
So tell us a little bit about Solarlytics. I want to make sure everybody's familiar with the company and what you guys do today and understand sort of where we're coming from.
Sure. So about 5 years ago, we stepped back as a group of founders and said, hey, listen, there's something fundamentally wrong with the solar industry. We see massive underperformance occurring at utility scale facilities really around the country. And so we created a company designed to really understand, to look deeply at why we have underperformance at the utility scale project level, and then to create a solution for it. And so we first spent time with customers analyzing specifically what was happening in the field, what types of underperformance were occurring, where they were happening in the field, and then of course why they were happening. And then we developed technology, both hardware and software, that can be installed in the field. We call it a platform that ultimately addresses it, instantly corrects some of the performance issues, but then it digitizes some of these older assets that allows us to collect data, analyze data, and ultimately provide actionable insights to the asset owner to continue to improve performance. So if you kind of step back and think about the company, one of our underlying missions and principles is to make sure that solar is performing at the highest level possible. We want to make sure that solar continues to grow and that investors and customers feel comfortable that solar is going to be there and deliver.
So today we're going to talk not just about what you guys are doing, but also you're also contributing to the broader discourse out in the community, right? So y'all, and you in particular, contributed to the most recent kilowatt hour analytics solar risk assessment, which I think they're on year 4 or 5 on, and it's always full of great information. Talk a little bit about, I think you guys were on page 13 or something like that, but talk a little bit about the content of that and what you contributed there to that effort.
Sure. So first, I want to applaud KWH. They do a great job producing this report and getting it out there for everybody to understand what's actually happening in the field. And I think they've done an excellent job illuminating the fact that we do have an issue. Right? I mean, last year's report showed that on average, utility scale assets are underperforming by 8% on average, right? So that means half of them are performing worse than 8%. Under their P50 levels, which is actually just abysmal if you think about it from a power sector technology industry. And so, by them illuminating it, it then kind of creates a platform and a forum for different companies and research groups to identify what they see is happening in the field. And so we participated this year to talk specifically about what we call voltage collapse as a particular issue. But if you go back and look at kind of some of the other issues that they've identified over time, it's actually very impressive. You're talking about string imbalance, inverter failures, O&M planning, other issues related with O&M, equipment related downtime, soiling, all that kind of fun stuff. So they do a very comprehensive job, I think, in identifying what the problems are and then bringing experts in to hopefully identify potential solutions.
They actually do. Jason and his team have always been very good at sort of pulling that information together. When they first started pooling all that asset data some years ago, we contributed then and continue to do so because just like you, we want to make sure there's answers to these questions. That's right. Now, I do caution people. I think the question that's often not asked is whether you're measuring from the right place to begin with. If we're escalating our estimates artificially, because those are leveraged, negotiated numbers that are part of the financial transaction, which is in fact the case, then it is much harder to hit those numbers to begin with. So we have to deal with that. Then once you deal with that, which is a nettlesome problem in and of itself and not today's subject, you put that to one side. Now what do we do about it in the field to get that plant to do the max that it's capable of doing in reality the way it physically sits, right?
Right.
And you guys came at it from a voltage collapse perspective, as I recall. Talk to me a little bit about that particular aspect. What is voltage collapse? What does that mean? What do you mean by that?
Sure. And before I dive into this, I think it's important to point out that, you know, the audience for this report is not only the entire industry, but investors in the industry, right? And so if you're an
Yeah,
investor and, you know, you're investing into a project and you're expecting this type of return, even if it's overestimated, you're still expecting this type of return, right? And if it's
yeah,
coming in substantially lower, then you're going to be upset, right? So the
yeah,
credibility of the industry is lost, obviously, if we overestimate. But there's
yeah.
obviously a lot of other issues that are affecting performance, and that's you know, that's, I think, what the highlight of the report really is focused on.
Yeah, for sure. I mean, I think getting the problem solved begins with our owners and financiers, asking hard questions and really making sure that the estimates that they are banking are and backing are real estimates. And it's not enough to say an IE, because I'll get this a lot of time. People say, well, an IE, agreed to the number. I'm like, yeah, an IE has agreed to every number the industry has ever had of the last 10 years, and they've all been wrong.
That's
So,
right.
move on from that. Make sure that it's as correct and conservative a number as you can in the transaction table, and then move from there.
Yeah.
Uh,
Yeah.
but voltage collapse. Tell me about voltage collapse.
Voltage class, absolutely. So, this is actually a fascinating
Digress.
issue. It's one we probably could have predicted as an industry, but didn't. And voltage collapse basically is a significant decline in voltage levels within a DC field. And as the voltage is dropping or collapsing, it falls outside of the range of the inverter, the operating range of the inverter. And so what effectively happens is the voltage drops so low that the inverter either is struggling to perform or it actually trips off completely. And so there's a number of different reasons for this that we're seeing in the field. And we see this really around the country, which is absolutely fascinating, Michael. So effectively, here's the operating range of an inverter. And you install your modules, somewhere in the middle, let's say, typically in the inverter. But over time, those modules are slowly degrading. And so they get down to the lower 25th quartile of the inverter's operating range. Then what happens is you have maybe a little soiling, or you have hot days. And when the temperature gets warm, all of a sudden the voltage production from those modules drops even further and gets outside of that inverter's operating range. And when that happens, that's voltage collapse, right? And then what you do have is you have this inverter struggling, and we see them tripping off for significant periods of time. And what's fascinating about this is it isn't just in the desert, in the hot desert of California or Nevada. We see it in Utah. We see it in Colorado. We see it in areas that have large temperature fluctuations, because in those areas you've designed the installation for some of the coldest weather temperatures. So your string levels may only be, let's say, 18 modules instead of 22 modules in order to accommodate those cold January, February days. But then all of a sudden you're getting warmer temperatures, let's just say in Utah, and above 90. And then all of a sudden you see this voltage collapse happening. So it's that range of temperatures that you're trying to design your solar array for. And when we see those high temperatures is when voltage collapse is occurring.
Yeah, I mean, that's the irony, right, of panels. The more sun, the more they produce, but also the hotter they are, the less efficient they are, right?
Yeah,
And
that's
so your voltage does fall off. And I think it begs a moment to, for people who don't know this, but IGBTs, which are the core, piece of hardware that's inside of all inverters and converters, have a voltage window that they're physically designed for. Some are broader than others, and they're efficient. The closer they are to the center of that window, the closer to the edges, the less efficient they are. And then if you get outside of that voltage window, it just doesn't work. And so that's what you're talking about, dropping out of the bottom of that voltage window, or even being near the bottom, where, if you're anywhere near the bottom, any sort of clouds or anything passing over is going to cause a shuttling on and off of that inverter, as it basically sees the thing and says, hey, you dropped out of the bottom, I'm going to shut down. Oh, wait, you're here, I'm going to start up again. Wait, you dropped out again. Wait, I'm going to start up again. Wait, nope, up. And it's back and forth, right? That's really noisy data. It's really inefficient, and it can really affect production. So,
and it affects, the inverter's, stability over the long period of time, right? I mean, you're beating up on the inverter much harder than it would otherwise. And subsequently, you have inverter failure issues throughout the entire industry. We blame the inverter, but in some cases, it's actually the operating conditions that the inverter is forced into that is taking its toll on its life.
yeah, I mean, when it's hot, you're running it up near the upper edge of that temperature range as well, right? That's where we see a lot of fan failures and things like that.
And we're seeing it. It's incredible, like in some of these areas. And again, let's just use Colorado or Utah, where you have these big temperature fluctuations. You're seeing voltage drop off at, let's just say 90 degrees. 92 degrees. And now all of a sudden you see these days where they're in the hundreds, 105, 110 degrees. And and there's just no way that the voltage is going to be produced at the level needed by the inverter. So you see a collapse, and we're seeing at some sites a loss of up to 30% of production due to this voltage collapse issue.
So now that we've gotten everybody properly alarmed and concerned about voltage collapse and all the problems with it, how do we address it? Like, what do you do? Right? What does an owner do if they're seeing these issues? And you can see it in the data, right? If you're monitoring a site. So how do they approach that problem?
Yeah, there's not an easy solution, to be honest with you. I mean, we as an industry put these modules out there in the field. There's no moving parts, warranted for performance, kind of, build it and leave it. But the truth of the matter is we're running into these issues. And so you need to add new equipment in order to stabilize that voltage. And so this is one of the issues that we decided to focus on as Solarlytics. We're on the DC side of these solar arrays. We're not on the AC side. But by focusing on the DC side, what you're really doing is you're addressing all of the inputs that are going into that inverter so that inverter operates as smoothly as possible. And so at least from our technology perspective, what we're able to do is, again, here's your operating range of the inverter. If all of a sudden you drop down here, we're able to boost the voltage and maintain the voltage at whatever level you want. Right. So this is a 1,000-volt inverter. You want to keep it at 720 volts. No problem. You'll never have voltage collapse. We completely eliminate it because we are constantly monitoring and maintaining the voltage at whatever level is appropriate for that particular site. So on a normal day, when it's hot, you're going to see drop off, and then boom, you're losing obviously production, but you're losing revenue. By maintaining it at that 720 volts, you've completely eliminated it. So there's new technologies that are available for kind of all of these issues, I'd say. But we've focused, at least from Solarlytics perspective, on maintaining the quality on the DC side. In this case, we're able to boost the voltage to stabilize the voltage collapse issue.
So that, we've had different applications of module level power electronics over the years that have addressed these types of issues in the resi and the light commercial space. Those have been too expensive to apply, at least historically, to the broader utility scale. Like, how, not to get too much into, Solarlytics and your product specifically, but is there another approach here that works for people with these bigger assets?
I think so. I mean, I love the module level approach, but it is just too expensive. And you don't really need to look that closely at utility scale assets. So think of what our Boost platform is really a string level optimizer, right? It's a DC-DC, it's a smart DC-DC controller. So we're able to monitor and control every single string that's coming into a combiner box and ultimately into the inverter, right? So we're able to stabilize. If you've got one string that's underperforming, we can lift that one up so they're all performing at that same level. So again, the inverter is seeing a consistent voltage level. So we can correct for the string imbalance issue. We can correct for voltage collapse. We can correct for soiling issues. We can correct for, so many of the other issues that you see on the DC side as systems age. And I think what's most important there is, you're looking for a cost-effective solution, right? You're going out to older assets. Maybe you have an O&M budget to clean the modules and cut the grass, but not much beyond that. So you really need to have a smart solution that's not expensive, but that's going to provide that kind of performance. And what we're also doing at the same time, which I think is critical, because again, we're going back to these older assets and making sure that they work well, is we're digitizing them, right? We're collecting data every 30 seconds at the string level, so we know exactly how every string is performing. We send that data to the cloud. We then use machine learning algorithms to analyze that data so we can identify what those specific problems are. So you as an asset owner now have improved O&M because you know specifically where the problem is, what the problem is, and is it cost effective to run a truck to actually fix it. So, I think the truth of the matter is, as we're going into these older assets and retrofitting them, we need to be making them smarter. We need to solve the problems that are there. We need to create solutions that are both helpful for the asset owner, so predictive maintenance and preventative maintenance kind of schedules, as well as alerts, and so that we keep these assets running as long as possible.
Well, you say roll a truck on these big assets. You typically have resident staff, right? DG or small scale utility. You're looking to roll trucks, and you're looking at that trade off on cost. On a utility scale site, it's less about the trade off in cost of rolling a truck and the cost of that windshield time to transit, and it's more about what is the priority for any given day, because there's always a lot of things going on a site, right? So where you talk about a solution that's basically optimizing the voltage as it comes in, sort of cleaning the power signals that comes in. Is that being implemented at the combiner box? Is that or at some load break disconnect if you don't have combiners, or is it being implemented between there and the inverter? Is that a piece of equipment that goes on the front end before you come into the inverter, DC bus? Like, what are we talking about exactly?
Yeah, we typically install between the string and the combiner box. Usually it's right next to the combiner box, to be honest with you, because that's where the strings are coming in. It's plug and play. Sure. We put a unit in there. We then connect right into the combiner box itself.
So does the combiner box turn into one input versus multiple at that point? Is there an architecture change?
No, the combiner box remains exactly the way it is, actually.
Okay. So, these are, as people look to retrofit sites, they have to understand like how much of a change physically this is. So is it the size of a combiner box? What's it look like?
No, it's smaller. I don't have a picture here. It's smaller. It's maybe, 3 feet by 2 feet by maybe 8 inches deep, something like that.
Yeah.
So it's smaller, but each of our boost units allows 8 strings to come in. And so we're then able to obviously manage each of those strings, and that signal that then goes into the combiner box and then ultimately to the inverter is reflective of those 8 strings all performing at the same level, right? So we're monitoring and we're controlling 8 strings at each of these boost units.
Gotcha. So I'm assuming you mentioned that it's communicating, collecting data, so it's got to be NERC CIP compliant, right? You've got to have some sort of a data connection at that point. So many of our combiner boxes today are not instrumented, so they're not smart. So you're going to have to come up with some sort of a wireless communication or something else. I'm assuming you've got all that stuff resolved, UL certs and everything else. Yep. How, from a cost perspective, if owners are seeing voltage collapse, like what? And I'm not asking you to quote people here, but like, what is you are the chief revenue officer. So I know this is part of your normal conversation. Sure. Like, what should owners expect from a cost perspective to try to resolve this? And then what kind of gains should they expect?
Yeah, again, it's super site specific, right? As we know,
of course,
every site is a little bit different, but all of our customers we're working with, we're providing less than a 4-year payback, typically less than a 3-year payback. So you're seeing an IRR of 35 to 40% at most of these sites, and which is obviously a pretty attractive investment opportunity for these guys. So our equipment, it obviously varies a little bit on kind of where the location is and all the rest, but it is eligible to the ITC. We actually manufacture in the United States, so it's eligible for the 40% investment tax credit. So that certainly makes it a little bit more attractive for those who can utilize the tax credit. But we have found that we're focused more on the IRR. We're focused on providing a solution for companies that frankly are finding that their systems aren't performing well. We want it to be cost effective. And so what we're really end up doing, Michael, in the long run is we're not just selling a box. right? We're selling
Yeah.
a solution that, is a combination of hardware and software. We have an MPPT patented software that is going to add an additional 2% performance gain from what you're going to see from your typical inverter. We've got other software that we push out to our units in the field that allow us to continue to both monitor, but also improve performance in the long run. So once you have that platform kind of in place, you're able to do a lot with the data, ultimately to improve the performance, improve the reporting, improve the O&M for the asset owner itself.
Okay. Is the data, just for my own personal, now I'm nerding out a little bit, is the data flowing, like is the DATs on the site or the historian on the site collecting that data, or is it going straight to your systems and coming back to the owner via a different path? I'm just curious.
Yeah, well, of course, the owner gets all the data from their inverter or wherever they end up measuring, right? So they've got that data. We send it straight from our units up to the cloud. We have a communications unit on site, which then goes to the cloud. We're then able to connect with the asset owner's SCADA system or whatever interface they're using, and integrate in seamlessly, effectively, so that they will have all of the data that's coming from our units, the analysis that we do on that data, all coming into their existing network operating center.
Well, it's an interesting solution and one that, obviously, like we talked about, module level power electronics have been around a long time. This is like moving, downstream towards the combiner box, but accomplishing a similar, function, which should make it a lot more cost effective and scale better for utility scale projects. So I think it's an interesting idea and something owners should really look at if they're seeing evidence of this.
Thanks. And the other thing is, I think as we get smarter as an industry, we're continuing to identify more and more problems, right? And we want to make sure that that these technologies are around for a long time. And what we're finding is, okay, modules are breaking. We have warranty claims on a certain portion of the modules. Let's replace those. Now we have mismatched strings, or we have an imbalanced field. With different modules, new modules and old modules, or your soft repowering, everything to kind of keep it moving forward. But that almost creates more problems. And so, a technology like ours, and there's others out there, but a technology like ours, which is going to balance those strings, will let you have those brand new, 600-watt modules sitting right next to the 300-watt modules, all feeding into the same inverter. And that's a pretty unique solution because we haven't been able to do that previously. And so when you had broken modules, either you were taking a couple of strings off, or you were restringing completely, which is super expensive, or frankly, you had mismatched strings, and that creates all sorts of problems, obviously, with respect to performance. And so, as we are, looking at these sites and say, okay, how do we repower them? How do we update them? How do we make sure we're squeezing as many kilowatt hours out of them as possible? It's technologies like the Boost platform that starts to enable new solutions and new ways to keep these projects online. It was interesting. I was just looking at the California RPS. We have to hit 60% renewable power production by 2030, right? So we have 5.5 years to hit 60%. And so it's great that we're building a lot of new plants, both solar, wind, and other technology. That's fantastic. Let's keep doing that. But it's also imperative that we keep every asset that we have right now connected to the grid operating at the maximum level possible, right? And that's what we're trying to do, is make sure that the asset base continues to produce so we can hit those RPS targets, so that solar and other renewables are considered reliable. That are considered something that we should be investing in. And that's, I think we're at a pivotal point right now in the industry where investors and some policymakers are kind of questioning, did we make the right move by investing so heavily in renewables? And I think the answer is going to be yes.
Yeah, look, it's a fair question. And we as an industry have to be able to answer those questions and be accountable. And that's ultimately what's going to win. What we can't do is just continue to do things the same way, not answer those questions and expect people to just continue to pump money into the industry, right? It's up to us to ensure that we deliver the promise of clean, reliable power, right? That's up to us. So given that,
clean, reliable, and quality power. And here's the other issue we're running into, and I don't want this to be a headline on, the Wall Street Journal or any place else, but, we're seeing serious harmonics come from,
Yeah.
solar arrays, not necessarily the big utility scale ones, but they do create some, but certainly those that are on utility distribution networks, right? And so you have community solar, you've got a lot of CNI solar, you've got just, some small utility scale solar. And if you've got those string imbalance issues, your inverter is switching very rapidly, and that inverter is creating those harmonics which are coming into the system. So we're working with utilities basically to say, hey, these are problem solar sites. Let's upgrade them, make sure that they don't have those string imbalance issues or the inverter isn't producing the harmonics. And the utilities are finding that that is a massive cost savings for them, rather than other solutions on the AC side, where they would need to put a new transformer in that may cost tens of millions of dollars in order to ensure power quality for their industrial and frankly end user customers, especially think data centers and those kinds of things. So yes, we want to be reliable, yes, we want to continue to produce, but it also has to be good quality power as well.
Yeah, and I think there's, so kind of stepping back a little bit. By the way, I agree with everything you just said. When we look at, we're sort of focusing on the DC end of things today in this conversation. So when we look at the DC end of things, upstream of the inverters, what other, sort of issues in the field do you guys see that owners need to be focused on, O&M operators need to be focused on? Like, what other types of issues are out there that we need to be addressing?
Yeah, I mean, one that we don't like to talk about either is inverter failure, right? So we have a pretty significant fleet of 600 volt inverters that were kind of the early day inverters.
Old architecture. Yeah,
old architecture. Well, there's no manufacturer of 600 volt inverters anymore. So people have been keeping them together with duct tape and doing everything they can to keep them going. But I've talked to so many asset owners, they're like, they're just dead. These sites are dead and we can't do anything with these 600 volt inverters. And so, what you can do is we can restring, again, crazy expensive. You're maybe creating more problems than you're actually solving. In some cases, maybe you can do string inverters, but again, more problems, and the reputation or what we've experienced with string inverters has been challenging over the last few years. But what we can do, of course, is the Boost platform is you install Boost and you install a brand new 1,000 volt inverter, right? So you're upgrading your inverter, very simple 1,000 volt inverter.
Which and then we're able to find too, the thousands now, but
we're starting to, yeah, right.
Yeah,
exactly.
Yeah.
But whatever the level is, right? And then we can boost the voltage to whatever level the inverter needs. And so it becomes a very cost-effective solution to keep some of these older assets performing, period. It's a lights off kind of situation when that inverter dies. And so we've worked with a lot of asset owners who just didn't have a solution, right? And even their O&M companies really didn't have a solution. So it's good to see that these types of technologies can have multiple applications, right? String imbalance and repowering and obviously voltage collapse, but also inverter failures and so many of the other issues we see in the field.
So you said string imbalance. Talk a little bit about string imbalance. Like what is that? What are people seeing in the data? What do you do about that? I mean, it begins kind of as a design issue, and then it plays out as these systems age. But like, talk a little bit about it for those folks who are tuning in and who keyed in on that are like, what's he saying there?
Yeah. String imbalance is probably the most prevalent issue we see at utility scale assets, and frankly, almost any installation of solar. But string imbalance effectively occurs when you have one string that's performing at a different level than the other strings that are going into an inverter. So again,
why does that matter? Like what?
Well, the inverter dumps. So here, let's say you have 18 strings all performing up here, and you have 2 performing down here. The inverter comes down to this lowest level and operates. And so all of that power that was created by these 18 strings is lost because the inverter is operating down here, right? And so instead of doing that and losing all that power, it's easier to raise up the voltage in this case of these strings so they're performing at this level. So the inverter is operating up here, right? So all that power that would have been lost is actually captured. And so string imbalance occurs from a wide variety of different reasons. It could be soiling, it could be vegetative growth, It could be the fact that one area of the field doesn't get as much wind as the other part. And so there's a temperature difference between these strings. It could be because you built it on a rolling hillside. And in these strings, solar noon is 1140, and these strings, solar noon is 1240, right? So now all of a sudden you create string imbalance just simply because that's the site that you had. And so it was almost by design, you had no choice. But those string imbalances, again, are being lost. And so, what we've decided to do here specifically is we create it's kind of two solutions. As soon as we install it, we automatically correct for string imbalance, right? We instantly boost up the voltage of all the respective strings so they're at the maximum level from a production perspective. But we also have a maximum peak power tracking algorithm that's dedicated for every single string. And so typically an inverter will have a single MPPT that's common to all strings, but instead we have one that's proprietary, that's patented, that goes to each individual string. So that string is going to be maximizing its production based on that MPPT alone. And then as it comes into our boost unit, if their voltage levels are off, we will then obviously lift the voltage. And so the inverter sees a very consistent level. And so the inverter, instead of, again, struggling and switching back and forth from all of these different inputs, is operating as efficiently as it can. And, we all buy inverters that say 98.5% efficient. Well, that's only under an optimal condition.
Yeah.
If you have these string imbalances, it's nowhere near 98% efficient. So we're trying to get it back up there so the inverter can do its job.
So it occurs to me, these upstream issues in most utility scale plants, which is where Origis spends all of our time, the lowest point of data is at the DC input to the inverter.
Yeah.
So, looking at the voltage, looking at like the harmonics, looking at power at a detailed level upstream of that point is not only hard without the instrumentation, it's darn near impossible. So how do people know? How do they find out? Like, how do they figure out that they've got this going on? Because to be blunt, it's not in the data.
Yeah. Yeah, I'm going to take my hat off to Raptor Maps. They do a great job, and the other drone companies do a great job of, taking a snapshot of what's happening in the field. And you can see, where you have module failure, and you can see some of the other problems, thermal problems that are happening in the field, but you can't see string imbalances. You can't see voltage collapse. You can't see some of these things on the DC side that that really do affect performance. I mean, again, they do a great job. It's a snapshot. But what you really need to do is be measuring constantly in order to see where those problems are. And so for those who put measurement units in at the string level, they have a huge advantage, right? You've started to digitize your field. And that's great. So now you have all this data. As long as you're analyzing it properly, you know what's going on. You may not be able to correct it, but at least you know what's going on. And that's where I think we've tried to differentiate ourselves, where we're not trying to create one part of the solution. We're trying to create a platform that monitors, right, and measures specifically at the string level every 30 seconds. We then analyze that data. And so again, data is great and it's powerful, but it's really not knowledge until you actually analyze it. All right. So you got to analyze it and figure out what's going on. And then more importantly is we have our box in there, which is the DC-DC high power controller, which is smart, which does all of the corrections, right? So to your point, taking a drone survey is a great first step. But if you see that you have problems, or frankly, if you see that your inverters are operating at different levels, like this one's performing as expected, and this one's somewhere south of that, or you're seeing, inverters trip off from time to time, that's a clear indication you have a significant problem. And to be honest with you, we actually get most of our calls coming from, kind of CEOs or investors who are saying we're not getting the kind of performance that we expected. We know the patient's sick. We don't know why the patient's sick. And so instead of taking an X-ray, we're going in and really doing a kind of a full blood work analysis and an EKG, and really understanding consistently where and why the patient might be sick. And then frankly, how to make those corrections. So,
well, look, I can't agree with you more on the overflight. I'll admit when we first started seeing drones being applied 2014, 2013, around that time period. I was not a fan. And it took me a while to eat my words and go, okay, yeah, this is a useful tool. And today we typically recommend to owners, like, look, do it quarterly. Don't do it annually. It's not enough, and it's worth it to do it quarterly. And so for you drone guys out there, that's what we're telling people. And if you've got a big enough site and you can afford it, having a persistent capability or having a terrestrial capability that provides you a persistent capability is incredibly useful in looking at these sites. And yeah, but what I heard you say was sort of like you have to sort of have somebody that comes and says, I have these known unknowns. I know I've got some issue. I don't know where it is. I don't know what the problem is. Can you come analyze it? Is there some, but that analysis can't happen post installation of the product. You have to have some idea of what it is prior to, or that investment never occurs. So speaking to the owners and the people that are listening to this right now and wanting to understand, how do I know if I've got a problem so I know if I need a solution? How do they go about figuring that out in a really clear, concise way?
So again, our approach at least is not to sell a piece of hardware, right?
Mm-hmm.
We really work closely with our customers as a trusted partner, for lack of a better word. And we sit there and we go through the as-built drawings. We go through last year's worth of inverter data. We go through as much data as possible to really identify specifically what those problems may be. And you can see pretty clearly through the data, if you analyze it properly, what some of the potential problems are, right? So you got the CFO who's saying, yeah, we're underperforming by 7%, or we're getting less than 7% than we expected, or maybe less than last year. That's great. But then once you get with the engineers and you sit down, you go through the data, you can identify at least some of the areas where we think we have a pretty significant problem, if it's voltage collapse, or if it's string imbalance, or if there's other inverter issues that are happening. And so the data's there. The question is, do people know what to do with it? Are they looking at it closely enough with the mindset of saying, hey, we know there's problems. Let's look at those anomalies that are occurring and frankly see what those problems might be. And the other problem, Michael, is when is that data collected? And inverters are collecting data typically, the older ones, maybe every 15 minutes, which is fine, right? If you're looking for, production data. But if you're looking for performance data, that's not nearly frequent enough. And so again, we collect every 30 seconds. And what we found with some customers is we had inverters that were dropping off, for minutes at a time. And over the course of the day, it would be almost an hour. And they said, no, we don't. And we said, yes, we do. When you look at 30
Just
seconds,
inside the interval,
it's going like this. But when you look at 15 minutes, it looks like a cloud went over, right? And so they're like, no, it's just a cloudy day, or we think it was a cloudy day. And so, having that kind of granularity is really important when you're trying to operate a 20 or 50 or a 200 megawatt power plant. I mean, it's what they would do at a natural gas plant, it's what they do at a nuclear plant, and yet we don't do it with solar plants yet.
Yeah, these sort of effects are below the, sort of day-to-day. O&M is a day-to-day thing. It's about keeping the site up and keeping it running and making sure, analyzing it sort of this level is really an engineering activity, and it's kind of outside the scope of break fix, preventive maintenance, ancillary services, and things like that. So working, what needs to happen is O&M operators need to have partnerships. They need to be working with their owner and saying, hey, there's this unexplained losses bucket here that I think we need to attack, and maybe we need to bring somebody in to look at the quality of the power on the site, which is really at a lower data level, and it requires some specific expertise. So it sounds like they need to reach out to Solarlytics, they need to reach out to some other folks and see what they can find out, because I can tell you, through construction, when they bring the equipment in and they hook it all together and they do the test, there's no quality of the power test that happens. That's not in a standard anywhere. That's not in anything that is a check mark on COD to bring a site online. It's not something that's incrementally done in any of the contracts. It's not contracted for, it's not planned for, it's not budgeted. It doesn't exist today as an ongoing sort of focus area. And I think what I'm taking out of this conversation as a whole, and I very much appreciate the time with you, and what I hope everybody else will take out of this as well, is there's this other area, the quality of the power, right? That may be affecting you, and there is a way to address it. And so reach out to Solarlytics, work with your O&M operators, try to find a way to define that undefined loss category that you're looking at in your monthly reports and attack it. And the good news is there's solutions available.
That's right.
And Rhone, I'll give you the last word. We're out of time, but that was sort of my summary of sort of where we ended up. But like, what do you have as a last bit of recommendation to folks sort of closing out this episode of Power Players?
Yeah, I think it's really kind of a vision of the future, right? All of these assets that we've built, that's great. Let's keep them running. Let's keep them operating at maximum levels. But increasingly, we're adding storage, right, to existing assets, not just new build assets. And that storage is super valuable. It's expensive, but it's super valuable because your PPA rates are higher. And frankly, we just need the storage. So I would say, let's, as an industry, be creative about the technologies that we're using. Let's really maximize the amount of generation we're getting from these older existing assets, because they are very, very valuable. Let's make sure we are spending the money on O&M and not just cutting the grass and cleaning the panels, because these are, frankly, the lifeblood of the industry. So we, as an industry, I think, have a responsibility to make sure things are working to the optimum level possible. But there's also a lot of money that's being left on the table if we don't go out and fix up these existing assets.
I couldn't agree more. Well, Rhone, I really appreciate the time.
Thanks so much for having me, Michael. I really appreciate it. Have a great afternoon.
Find more information on this topic and more insights on clean energy at origisenergy.com.